Okay, we are going to just pick up where we left off yesterday. I just want to talk about water because we just raced through it at the end there. So these notes you guys should have already taken. I just can't reiterate enough the importance of water. Obviously, I think we all know how important it is. I do think where we live in the land of 10,000 lakes, which, as we all know, is not true. It's actually more than that. So it's such a weird thing for us to even think about issues with water or loss of water. And we are not normal in that sense of having an excess amount of water. When you really go to most locations on the world, access to clean drinking water is actually not normal. So, water, obviously, we all know, is super important, primary reason for life. Yesterday in the video, and I'll also mention it briefly, the water molecule, when you look at it individually, is a polar molecule. That oxygen side hogs electrons, the hydrogen side has less electrons, so it's more positively charged. So it gives water a lot of really unique, cool features that we may not be so familiar with. So when water sticks together, that's cohesion. When it sticks to itself, what's the importance of that? It's what allows materials or allows water and materials, the nutrients, to be transported in plants and animals. Water has a resistance to temperature change. I'm going to show you a video here in a second what that means. That's really important environmentally. Water is something on our planet that plays almost a central role besides our atmosphere regulating temperature on Earth. Ice density. Ice is less dense than liquid water. That's the reason it floats to the top, insulating the lake underneath, allowing the animals in the lake to stay alive, the fish to stay alive. And another cool thing that it also happens is when that ice melts, it does allow nutrient cycling in the lake in the springtime. Water is the universal solvent. Because of water's polarity, a lot of things dissolve in water. Going back to that, can transporting nutrients and things. So that water hanging on to temperature is really important. I found a super easy younger video here, obviously sort of to explain what we actually call the specific heat of water.
Hello, and welcome to another ADLC digital lesson. Today, our lesson is on heat capacity. If you've ever been to the beach, you know that the sun can really heat things up. So much so that the sand can get too hot to walk on. But you can always cool your feet off in the nice cold water. But it gets one thinking, why is the water so much colder than the sand when they are both getting heated by the sun equally? And the answer has to do with heat capacity. Sand has a very low heat capacity. Water has a very high heat capacity. That means you have to heat up water an awful lot before the temperature goes up. Sand only has to be heated a small amount before the temperature goes up. So a small amount of heat from the sun can make the sand very hot. The difference between these two substances is huge. You could add tons and tons of heat to water, and it will resist temperature change. You can kind of think of water as having a large trash can for heat. You can put a lot of heat into the trash can before it fills up. Sand would have a very tiny trash can. It can't take much heat at all before the temperature goes up. Again, that is because water has a very high heat capacity and sand has a very low heat capacity. Now we can prove that water has a high heat capacity by doing a simple experiment. Here we have 5 substances: water, wet dirt, dry dirt, wet sand, and dry sand. We're going to compare the heat capacities of these substances by heating each one of them up and recording the temperature. First, we'll start with sand. We do this experiment by putting a temperature probe into sand inside of a pie plate. Then we put the whole thing under a very hot heat lamp for 10 minutes. When that's done, We repeat this with all the different substances. And when we're done, we get a graph that looks like this. Now, if you look very closely, you will see that the graph shows that the water didn't change temperature very much at all. But the dry sand changed temperature quite a bit. It went from 20 degrees all the way up to 54 degrees when being heated for the 10 minutes. Water, on the other hand, only changed temperature a few degrees. Why? Well, remember, water has a very high heat capacity. You can add a lot of heat to water before the temperature will go up.
One of the cool things they do with using water and the fact that it's high heat capacities, I don't know if you guys have seen any of these greenhouses that they make now that actually have, you take barrels of water and put them in the back of the greenhouse, or you place them throughout the greenhouse, and during the daytime they're getting heated up from the sun, especially because it's in this black barrel, and then at nighttime they just radiate all of that heat out because, like we just said, water has that high specific heat capacity. And even in our area, you can literally have, if you have it set up properly, you can have a greenhouse that stays warm year round and actually
and what?
Food year round. Acids, bases, and pH. So most of us are familiar with the pH scale. pH scale, remember, tells us about the acidity or alkalinity of a solution. It goes from 0 to 14. Items on the scale that are less than 7 are acids. Items that are greater than 7 are bases. Some of the characteristics of acids, remember, they're sour if we eat them, but the big thing is they corrode metals. Every living organism has a certain pH that they need to have internally, that they need to be living in. As we all know, when it's a real excess pH, even for us, like if it gets on our skin, it can damage tissue, right? But if you look at this one, it's a little more specific, obviously, to environmental effects, maybe something you haven't seen like in chemistry class before. But you can start to see if you have a pH of a lake that's starting to get around 4 because you have acid rain in the area and that lake starts taking on too much of a high pH, or a low pH, those fish are going to die in the lake. You can literally have complete die-off. pH of 5, organisms before that, so you can see frog eggs, tadpoles, crayfish, mayflies die as soon as it hits that pH. Rainbow trout, they definitely don't like the low pH there. Rainbow trout at a pH of 6. So acid in the environment is not a good thing. So besides the fact if you get a lot of it, it's going to kill tissue, but if it gets to a certain level, you're going to have die-off of organisms. So lesson 2 is all about systems in environmental science. And the definition for systems is long. The ironic thing is the relationship that exists in systems is also technically long. It's really complex. Any sort of a system, when we're talking about the environment, is a network of relationships among parts, elements, or components that interact with and influence one another through the exchange of energy, matter, or information. It's almost like, just think of this sort of entity where you have things coming in, you have things going out, and there's just so many complexities to the system that if you have one change in that system, you don't even realize how many other things that can be affected because there's just things that you maybe didn't even think of. So Earth's environment consists of really complex interlinked systems. Even looking at this picture here, we see some trees, some grass, maybe some, small shrubs down there. It is a very complex system when you start looking at the amount of sunlight, the pH of the soil, what type of rain is falling there, what's the amount of rain that's falling there, what type of organisms live there. Do you have, let's say, deer that come through and eat possibly younger trees? Do you have bears that eat, the berry plants in there or the blueberry plants? So systems are very complex. Systems do not have well-defined boundaries. If I take a look at this lake here, there isn't a defined boundary. We don't have this, area where we can say that this system stops here and it ends there. You can have this exchange of energy, matter, and information with other systems at any given time. Mrs. Escalay has a repeat there, sorry. I mean, if anything, I just hope you guys are like tuning into the fact that this is really complex. It's not always even just what we see on the surface. So when we look at these things, we have what's called inputs and outputs. So inputs can be things like energy, information, and matter, and outputs, think of like, what are we getting out of these things, right? So using the Gulf of Mexico, for example. So think down, like in Texas there. In the Gulf of Mexico, if you were to look at that system, so that body of water, you have fresh water coming into it, you have sediments coming down from the Mississippi River, you're going to have nutrients coming in, you're also going to have pollutants, because think of that, the Mississippi flows into the Gulf of Mexico, so every single bit of pollution that comes into the Mississippi River is going to eventually make its way down in the Gulf of Mexico. But we as human beings, we take something out of that, right? We get fish out of there, we get shellfish, shrimp, scallops, other things. So if any of those inputs are affected, our output that we get out of it can also be affected. The pollution that we put into it, those sediments, all of those things can affect what we get out of it. So inputs are what put into the system, outputs are what we get out of it. Feedback loops. We have two different types of feedback loops. What a feedback loop is in general is what we were just talking about. So an input and an output. That's a feedback loop. You have one thing getting put into the system, one thing getting put back out. Negative feedback loops are probably the ones we're most familiar with. So a negative feedback loop, the output of a system moves in one direction, acts as an input that causes the system to move in the other direction. So what happens is the input and output respond to each other's effects, eventually canceling each other out and then essentially stabilizing the system. Most systems in nature are negative feedback loops. Got to throw in the example of a thermostat though, because most of us are familiar with our thermostats in our house, right? Maybe you have it set to 68 degrees, 67 in your house. Your house has a negative feedback loop. So if it gets too cold, the furnace will kick on, or whatever type of heat you have. If it gets too hot, the furnace will kick off. So you have an input and an output response there. Most relationships in nature are negative feedback loops. So think of all of the predator-prey relationships that exist. Think of how many we have in our area here. Think of coyotes, white-tailed deer, wolf, white-tailed deer, fox, the ruffed grouse population. Those are all negative feedback loops. Here's another example of animals that we have in our area. So bobcats and then rabbits. If we have an abundance of rabbits, so if you have a lot of them, it can support a lot of predators, right? But the problem is if you have too many predators, they're going to start depleting the population. There's that input, too many predators. I'm going to deplete the population of rabbits. Now I don't have enough food. So now that cannot support many predators, and then you go back to few predators. When we're back to few predators in the area, then you're going to have abundant prey in the area. So you can start to see how complex this is and important it is to always kind of make sure the system is working the way it's supposed to, because it will, if sort of left to its own course of action, will sort of stabilize itself and correct itself. Now, positive feedback loops, even though it's called positive in environmental science, they are often not positive and can really do bad things to the environment. So positive feedback loops drive systems to the extreme. You just have one thing that happens and essentially nothing that happens after that. That's just sort of don't think of positive like yay positive. It's just one thing that happens and you don't have something else coming in behind it. If you have a ditch in the picture here, so if I have a ditch, and let's say we go ahead and I don't like any of those plants, so I'm going to go ahead and clear away all those plants. And people do this, think about this, they do this a lot in lake homes, right? They want to see their beautiful view of the lake. So they will come through and they will clear all of the trees out. The problem is now you've exposed more soil. And what happens when we just have soil and we don't have plants there? Plants drastically help with erosion or preventing erosion. So if you don't have plants, it's going to have increased erosion. You're going to have more soil that is moved away by water, wind, ice, and gravity. You're just going to have this really bad outcome. So it's that balance there too. So positive feedback loops, generally in the end, not good things are happening, can alter systems dramatically. The last thing in this section talks about Earth spheres, and I'm guessing you guys have heard of most of these. Your book kind of breaks it into 5. Everywhere else you look, it's 4. Geosphere, geo meaning Earth, right? The geosphere is all the rock at or below Earth's surface, all the rock. Geo, Earth, rock. The lithosphere is the outermost layer of the geosphere. So the outermost layer, essentially the hard rock on and just below Earth's surface. The biosphere, bio meaning life, right? All the plants, living and non-living parts of the environment. So think of everything that's alive. It's essentially half of the world that we live in, right? Because the other half that we live in is the atmosphere. So the atmosphere is a layer of gases surrounding the planet. And then why did Mrs. Escalade put another biosphere in there? All water on Earth. Oh, it's because I have a typo. All right, this is supposed to be hydrosphere, guys. This last one here. So hydrosphere, all the water on Earth's surface, underground, and in the atmosphere. I should know that. I love water, right? So hydrosphere, do not write biosphere in that back thing. It's supposed to be hydrosphere. Hydro meaning water, right? And there they are. There's our spheres. In the next section, we're going to get more into detail in talking about them because that's really what environmental science is, right? It's talking about all of those things.